Well, hello everyone, and welcome to Lecture 8 of the Building Planets series. This one about plate tectonics and planetary atmospheres. But first, as ever, let's quickly review last lecture, which was comparing the rocky planets of our solar system. Mercury, extreme temperature range, no atmosphere, possible graphite flotation crust on its magma ocean as its first crust, quite amazing. Venus, hot, 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 hot all the time. Thick carbon dioxide atmosphere, possible carbonatite rivers in the past to create those channels, amazing. Earth, average temperature just above water freezing, and unique nitrogen and oxygen atmosphere and unique plate tectonics. And then Mars from a pleasant 70 F down to minus 200 with a very thin carbon dioxide atmosphere, and atmospheric pressure that goes up and down by 30% over the course of the seasons as the polar caps freeze out and then sublimate back into the atmosphere. So some of those things are going to be relevant today: the plate tectonics angle and the atmosphere's angle. All right. So what is plate tectonics, and why haven't we so far found it on any other planet? How does plate tectonics help maintain and preserve atmospheres, and how do other atmospheres evolve on other planets without plate tectonics? So we're going to talk about working up to plate tectonics. How do we think that plate tectonics might start? Lots of hypotheses, not so many answers. And we're going to talk about volcanism and plate tectonics and atmospheres all together in addition. Here is a cross section of the Earth. And in this lecture, we'll mostly be talking about the very top two layers in blue, the crust and the mantle lithosphere. And I'll show them in more detail in the next slide. It's just the thinnest top part of the planet. And below that, of course, is the rocky mantle all the way down to the core mantle boundary. All right, here is a simple model of the temperature and viscosity of the Earth's lithosphere and mantle. Let's parse this and we'll study each part in turn. First, let's look at temperature. Temperature with the dotted line and the scale at the bottom. The surface temperature is relatively cold up at the surface where we walk around, and the temperature rises all the way down to this line, which, and we'll see at the moment that in a moment that line is the bottom of the tectonic plate. At the same time, the viscosity, which is the solid line, and the scale at the top, that is the viscosity, the thickness or the willingness to flow of the material, is high near the surface. The material is very stiff. In fact, it's brittle. It doesn't flow. But with increasing temperature and pressure, the material, because it comes down in viscosity. None of it, important to remember, none of it is liquid. Now, the uppermost part of the lithospheric plate is the crust, made of many kinds of rocks that are the result of many processes, including volcanism and pressure and heat and sedimentation. And below that is the mantle lithosphere, which you see in this little cartoon. This is mantle material that's cold enough and maybe depleted by melting that it's just stuck to the crust. Underneath the lithosphere is the mantle. And the crust is between, say, 5 and 100 kilometers thick, more or less, thin at the thin end for oceanic crust and thick for continental crust. And the mantle lithosphere can extend all the way down to 400 kilometers under thick, cold continents. Now, the crust and the mantle lithosphere together, simply called the lithosphere, and I'll use that word, generally moves as a unit. That's the tectonic plate. And underneath the mantle convects. That is, warmer mantle rises toward the lithosphere, conducts out its heat, and then when it's cooler, it sinks again. And finally, let's look over here at this lowest viscosity channel underneath the lithosphere. This is the uppermost convecting mantle, known as the asthenosphere. Its notably low viscosity is probably due to a small amount of water being present in the minerals there. Even a few tens of parts per million of water, or OH, hydroxyl, trapped in crystal defects of otherwise water-free minerals in that upper mantle can reduce their viscosity by an order of magnitude or more. And the asthenosphere is critical to the action of plate tectonics. That slidey layer allows the lithospheric plate to decouple from the mantle and move. Listen, so viscosity is so cool that I can't resist talking about it a little more. I've always loved this so much. So let's look first at this part in the yellow box. Viscosity, which here I'm calling eta, is defined as shear stress, which is sigma, divided by shear rate, which is epsilon. And so let's talk for a moment about what that means. The shear stress is the external force acting on a surface parallel to the surface. So look at my hands, the shear stress of my hand going over my other hand. And the shear rate is the rate at which this material underneath deforms as it's sheared. And so viscosity is the relationship between how hard the shear stress is and how much the material deforms in relation. So it's a way of saying how flowy is this? At the top right, the Newtonian viscosity box, the material deforms the same amount no matter the shear stress. Shear stress doesn't change the viscosity of the material. So that's kind of an ideal material. In the bottom left shows a Bingham material, which I think this is very, very interesting. The Bingham material doesn't deform at all until a certain shear stress is reached. And so here's shear stress rising, 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 but no deformation is occurring. And then once that critical shear stress is reached, then deformation begins. Paints and toothpaste are designed to be Bingham materials. So think about wall paint. When you're shearing it with your brush, the viscosity goes down and it spreads. But when you stop brushing, that is, you stop shearing it, the viscosity stops being low, and then the paint is less likely to drip. So that is a Bingham material. Now, finally, the bottom right, mantle materials. They have a power law viscosity. Shear rate rises as a power law of shear stress. So now imagine that high viscosity lithosphere sliding across the low viscosity asthenosphere, that top of the mantle, and that shearing action actually causes the viscosity of the asthenosphere to even drop further and allow the plate to move better. I think that is so interesting. All right. So here are the main plates on the Earth. Note that their edges rarely follow the edges of the continents. This is a common misconception. Now, if you look around here, you see the edge of the plate going right down the middle of the North and South Atlantic Oceans. It does not go right along the edges of the continents. New crust is being made by mantle upwelling and melting and magmatism in the middle of those oceanic basins, and that is the edge of the plate. This is part of the plate tectonics engine. Notice also that the plates are hard to identify without information like magnetic measurements, earthquake measurements, examination of the geology. This map was not made by aerial observation. I point this out quickly because it's hard to see on other planets. So why do plates move? So we figured out what plates are, but why do they move? It turns out that they're not pulled along by the convection of the mantle underneath them. They move for two reasons. They move because of ridge push and trench pull. Mid-ocean ridges are raised. Here you can see a mid-ocean ridge on the left. Mid-ocean ridges are raised relative to the surrounding ocean floor because ocean crust is thin there. In fact, it's just being made and everything is hot. As the newly made oceanic crust slides away from the ridge, it cools and it obtains lithospheric mantle sticking to its bottom, and it actually slides down away from the ridge. So that is ridge push. On the other end, over here, where oceanic crust runs into a thick, buoyant continental crust, for example, the more flexible and dense oceanic crust gets pushed down into the mantle, downward here in the subduction zone. The density of the oceanic crust sinking down actually pulls the plate down. That's trench pull, and that's subduction. Notice that there is a trench, a low point, where the subducting plate goes under the continental plate. These are the deepest known places on Earth, the deepest places in the ocean. And notice that behind the trench, mountains are built, and they're built partly from scraping the plates together, scraping sediment off of the downgoing plate, and partly from volcanism. And that sequence, the trench and then the mountains, will come up again later when we talk about Venus. Now, there's a place on Earth where the mid-ocean ridge, the divergent plate boundary, where new plates are being built and sliding away from each other, actually comes above ground in Iceland. So it's not exactly hot and volcanic in this picture, but here our friend Sam Bowering is actually standing between the two plates. Volcanism is episodic and it's on a long period by human standards, but this is actually a plate boundary that you can stand in, which I think is so incredible. And even more incredible, this gap in the plates actually goes below water, and you can snorkel in this lake and you can swim between the two plates. And that's just an amazing thing. And you can find fabulous color photos of this phenomenon and even tourist packages so that you can go do it. So how does plate tectonics start? That is our next big question. First, it's a bit of a race against time. In the magma ocean and in the early Earth lectures, we talked about how quickly the larger rocky planets cool after their final accretionary impact. But think of this, production of new plates means moving plates, and moving plates require that thinner oceanic plates are able to subduct under thicker plates. Otherwise, there's no relative movements between the plates. And at the same time, as the planet is cooling, the lithosphere is thickening. It's thickening by cooling. More mantle lithosphere is getting stuck to the bottom. The cooler the planet gets, the thicker and more viscous the mantle lithosphere becomes, and that thickens the plate and makes it inflexible. And we think that planets start with what's called a stationary lid. That is, they're effectively one plate planets. So if the planetary lithosphere gets too thick before it starts breaking and moving, plate tectonics won't be able to start. And there are a couple of chicken and egg style problems, quandaries about plate tectonics. One chicken and egg quandary, looking back at this picture, involves the asthenosphere, that low viscosity channel under the lithosphere. Importantly, its low viscosity, as I mentioned a few minutes ago, is partly due to a small water content. But one of the main ways that water gets into the upper mantle is through subduction of wet oceanic plates. So this material go down right here carries water with it, partly bound up in mineral crystals and partly probably a little bit of liquid water. And then it's released into the asthenosphere right here in the wedge above the plate. And so if subduction requires wetness to work, but subduction is also the way the wetness is acquired, then how does that happen? One hypothesis is that the planet formed with some water in its mantle, the way our magma ocean solidification models indicate. But if that's so, then every rocky mantle planet should be damp enough to start plate tectonics. Why don't we see it unequivocally on other planets? A note on this at the end, but suffice it to say now, the size and bulk composition of the planet also seems to matter. But let me give a caution. No one actually knows for sure how plate tectonics starts and why Venus and Mars don't have plate tectonics. They don't seem to have plate tectonics. There are a lot of ideas to prove a hypothesis with only one example. So that said, here is one idea of how plate tectonics starts. The line at the top, first of all, shows surface plate velocity, U prime of the surface plate velocity. In this image right here, there's no plate movement, so that line is absolutely flat at 0. The block of colors underneath is a graph of the whole mantle from the surface down to depth, and the colors indicate compositional density left over from the magma ocean stage. This image shows a transient period of stagnant lid convection. So stagnant lid meaning the plates aren't moving, and convection is the transfer of heat. And this transfer of heat, this mantle convection, builds up damage in the lithosphere. It's straining the lithosphere. That is, the lithosphere is strained and faults and breakage occur. This is a key idea, and people who are studying this really focus on this problem. For plates to exist, the lithosphere has to break along faults. If the lithosphere is too warm, then breakage anneals away, it heals before movement along those faults can begin. And so can faults exist when there is a lot of heat? Really not known quite what those boundaries are, but people are certainly working on how hot can the surface be and still maintain faults. So here is when the initiation of subduction or something like subduction has begun, when sufficient damage has accumulated in the lithosphere that shear zones and plate movement occurs. So you can see in that top graph that U prime, the surface velocity. There's positive velocity in some places and negative velocity in others. And so it's actually moving, the plates are moving. It's not really subduction though, it's a kind of a blobby foundering of the lithosphere. This process, which does produce this kind of sluggish blobby subduction, can be initiated by big impacts or by the initial overturn of unstable mantle layers immediately following magma ocean solidification, which is something we talked about in the magma ocean and lunar lectures. So the style of subduction in the Hadean, that is before 4 billion years ago, was likely different than true plate tectonics. Downwellings could be more drip-like than slab-like, and lithospheric deformation changes in the lithosphere would be more diffuse, owing to the effects of more rapid annealing because of the hot surface. However, subduction and protoplate motion could happen. And so this is an idea about how early plate tectonics might start and what it might be like. Some people call it a kind of blob subduction, drip subduction, sluggish subduction. So some kind of plate tectonics probably did occur pretty early on. Now, how does plate tectonics influence atmospheres? Well, two main ways that I'll mention today. There are, of course, a lot of nuances and many processes to consider, but two main ways I'm going to mention today. First, volcanic degassing. Isn't this a great photograph? This is the great eruption of Lassen Peak in Northern California in 1915, as you can see written by hand in the bottom of this photograph. It was taken about 50 miles away. Now, there is a lot of gas driving that volcanic ash up into the sky. And so that's the first thing. Volcanoes are largely, but not entirely, largely a product of plate tectonics on the Earth, and they release into the atmosphere gases from the magmas that they carry from depth in the Earth. And so they take gases effectively out of the mantle of the Earth and put them into the atmosphere. So that's the first way that plate tectonics influence atmospheres. And the second way is carbon sequestration in rocks and in oceans. But first, more about those volcanic gases. The main gas that volcanoes release is water. You can see in this estimate, it's 70 to 90%, but they also release a lot of carbon dioxide. And that is an interesting point in today's world. The ratio of these gases can really be very different among eruptions. And one thing that one eruption I'm quite fascinated with, a lot of us are, is the Laki eruption in Iceland in 1783, which released an inordinate amount of sulfur, which actually caused extreme cooling in the northern latitudes. And this eruption also released fluorine, which killed vegetation and sheep and caused a vast famine in Iceland. It's even been suggested that the famine in Europe caused by the extreme cooling from sulfur actually helped start the French Revolution. But back to carbon dioxide. If volcanoes are producing it, why doesn't it just build up and build up in the atmosphere? Well, here's a cartoon of the carbon cycle, a cycle that allows Earth to moderate its climate, but a cycle that has failed on Venus, importantly. On the left, carbon dioxide is released from volcanoes. And on the right, the constant action of plate tectonics pushing up mountains and creating new crust makes a constant reservoir of fresh rocks to weather away by the action of rainwater and temperature and chemicals on the surface of the Earth. And so this constant supply of fresh rocks and the weathering actually takes carbon dioxide out of the atmosphere and delivers it into the oceans, where it ends up as a sediment and then is carried back into the mantle through plate tectonics. So that's a cycle that moderates how much carbon dioxide is in the atmosphere by constantly bringing it back down via weathering into the Earth's mantle. I just want to make a point, because carbon dioxide in the atmosphere is such a big deal right now because of climate change, which is a very significant threat to all of us here on Earth. I am going to just talk briefly about that to make sure that there isn't any misunderstanding. Volcanoes are not the major source of carbon dioxide in our atmosphere. It's us, it's humanity that is the major source of carbon dioxide in our atmosphere, and our production of carbon dioxide has overwhelmed this carbon cycle. Models for the temperature effect of human activities, shown here in the orange band, fit the temperature data on the Earth, which are the small black symbols, fit the temperature data very well. The temperature data cannot be explained by solar forcing variations or volcanic contributions, which can be seen at the bottom in blue. That natural forcing, the forcing of the sun and the forcing of volcanoes on surface temperature, creates fluctuations. It doesn't create the long-term rise. According to the US Geological Survey, the world's volcanoes, both on land and undersea, generate about 200 million tons of carbon dioxide annually, while human activities release about 24 billion tons of carbon dioxide every year. So the humans produce 120 times more carbon dioxide than are produced naturally. So volcanoes absolutely produce carbon dioxide, and plate tectonics absolutely helps mediate the atmospheric composition. So the question is, what happens on other planets? Well, here is Europa, a moon of Jupiter and a possible site for life. It does seem to have a kind of ice plate tectonics. Mars has some very small indications that it might have had plate tectonics in the distant past, but mainly there's very little evidence, and very few people think that Mars had plate tectonics. And as far as we know, Venus does not have plate tectonics like the Earth's. So why not? Venus has the same size, more or less the same composition, the same distance from the sun. So here are some of the best ideas why Venus doesn't have plate tectonics exactly like the Earth. Maybe too dry, so no low viscosity zone, no asthenosphere to allow plate motion. Maybe too dry, the lithosphere is too dry, which makes it even stronger and harder to break into faults. Maybe too hot on the surface, so the faults heal instead of remaining breaks, allowing the crust to move. But there are some people who see features on Venus that are convincing to them that they're plate tectonics. Here's a really cool example comparing the Aleutian Trench on the left and some great Magellan mission topography of Venus on the right, showing a similar kind of arc. So beyond just the similar visuals, which are not convincing, right? I mean, they look similar, but who knows if they are. The topography across these features is extremely similar. So recall that there's a trench when you go across an Earth subduction zone, and then you go up onto mountains. And it's exactly the same in Venus in this example as it is on the Earth. And there are many other such features like this. So maybe Venus does have plate tectonics of a sort. So how do planets without plate tectonics keep their atmospheres? So this is the last point I want to make in this lecture. Even without plate tectonics, planets can have volcanism from hot upwelling plumes like these. And these hot upwelling plumes occur with or without plate tectonics. They happen on our Earth as well, and we think that they happen on Venus and on Mars. There's evidence for these, and they would release gas into the atmosphere. You can also have drips from the lithosphere, which incite an additional kind of volcanism, and it would also release gases into the atmosphere. And neither of these mechanisms need plate tectonics, and they may help to account for the ongoing atmospheres on Mars and Venus. These volcanic moments can add to the atmosphere, but then the planet also needs enough gravity to hold on to what it's got. So there we are. Early in Earth history, it looks like there are multiple working hypotheses for making blobby, sluggish plate movements. And now, plate tectonics and its attendant volcanism and mountain building creates a carbon cycle where the atmosphere is replenished and the carbon is drawn down via reaction with new rocks, leaving the Earth's atmosphere at least to be rich in oxygen because of life and nitrogen because of its fundamental composition. And so that is what allows us to breathe, all of us air-breathing creatures on Earth. And finally, there may be some plate tectonics on Venus, but none on Mars or Mercury. So next time, what is a habitable planet? The final lecture in this series on building planets. Thanks so much for joining today.